Alright guys, we're going to go over the Chapter 1 study guide today. And before we get started, I just want to say something about these videos that go over the study guides. I hope that you first try to do the problems on your own first. And then if you need a little bit more help or you get a little confused, then you turn the video on and see how to do the problem. But I really think that if you're just writing down the answers as I'm writing them down, it's not going to help you so much. So please try it on your own first, give it an honest effort, and then if you have a little bit of trouble, turn the video on and see how to do the problem. So, okay, let's get started. First of all, with the vocab list here at the beginning of the study guide, you guys have the vocabulary list in the workbook. So I'm not going to go over these definitions, but in your own words, okay? So in your own words, write the definition for these vocabulary words. So let's jump down to the first problem here on the bottom. It's on the periodic table. Okay? And it says, fill in the periodic table below with as much information as you can remember. And so here's what I would expect you to know by now. Let's go with the family names first. So this first group is the alkali metals. The alkali metals. The second group is called the alkaline earth metals. Alkaline earth metals. Alright, and then we've got this block of elements right here. This block of elements is called the transition metals. So we label those. And then we've got a couple more family names. Well, actually, let's go down to this. These two rows at the very bottom of the periodic table. These guys are called the inner transition metals. The inner transition metals. So they're called the inner transition metals because they really should fit in the periodic table right there. But if they did that, that would expand the periodic table so long that it would take up so much space. So they pull these two rows of the periodic table out and put them at the bottom just to save space, but they're called the inner transition metals. A couple more families. Over here, group 17, these are the halogens. And then group 18 is the noble gases. Okay, so hopefully we know all the family names. Now let's go over a little bit more information on the periodic table. So this bold line right here, I refer to it as the staircase. The staircase, so let's put that. The staircase separates. Above the staircase are the nonmetals. Okay, below the staircase are the metals. And if it's touching the staircase, we call them metalloids. Or some people refer to them as semi-metals. They have properties of metals and also some properties of some nonmetals. Okay, so that's pretty much it for the names. Now let's go to charges. Okay, this first group has a charge of +1. Second group is +2. Now the transition metals can have a lot of different charges, so we don't really know for sure, so we skip the transition metals. Group 13 is +3. Group 14 is ±4, and then it goes to minus, so -3, -2, -1, and of course the noble gases, they are not going to give up their electrons or take any more on, so their charge is 0. Alright, now let's do valence electrons. So group 1 has 1 valence electron, so I'm going to put 1 VE. Group 2 has 2 valence electrons. We're going to skip the transition metals. Group 13 has 3 valence electrons, and it just keeps going up. So 4, 5, 6, The halogens have 7 valence, and the noble gases have 8 valence electrons. Except for helium, which just has 2 valence electrons. Because there is only 2 electrons in the atom. Everything below helium, though, will have 8. Okay, is there anything else? Let's see. I think we should label this. So silver, which is Ag right here, has a charge of +1. Always has a charge of +1. Zinc, which is right here, always has a charge of +2. And then aluminum always has a charge of +3. So there's a couple of transition metals that we do know the charge of. Silver's +1 and zinc is +2. And so if you put a box around these three, I think we did this in class, to help us remember. Also, there's tin and lead. So tin is Sn and lead is Pb. These two can have different charges or different oxidation states. So when we name them later, we're going to name them with the same rules as the transition metals. And I'll show you what that's like here in just a bit. So if you can remember that from the periodic table, I think you're doing pretty good. So let's go to the second page of the study guide. Okay. So chemical bonds on this page, it says for each of the following compounds or molecules, identify whether they are held together by covalent, ionic, or metallic bonds. Before we start this, I want you to make a note on the top of this page. So we've talked about 3 different types of chemical bonds. We talked about ionic bonds. We've talked about covalent bonds. And we talked about metallic chemical bonds. So let's make a note, and I think this will help us with this section. Ionic bonds are formed between a metal and a nonmetal. Covalent is between 2 nonmetals. And metallic is between 2 metals. So when I say 2, it's at least 2. It can be more than just 2, but at least 2. All right, so let's go through this. Number 1 is sodium chloride. Sodium is a metal, if you look on the periodic table, and chlorine is a nonmetal. So if it's a metal and a nonmetal, it's held together by ionic bonds. Okay, let's go to number 2. It has carbon, hydrogen, and oxygen. If you look on the periodic table, these are all nonmetals. And so if we look up here, the nonmetals is covalent bonds. All right. Number 3, carbon dioxide. Carbon's a nonmetal, oxygen's a nonmetal. So again, nonmetals is covalent. Number 4, potassium nitrate. So potassium is a metal, nitrate is a polyatomic ion, but they're all nonmetals. So metal, nonmetal, and that'd be an ionic. Okay, number 5, we've got iron oxide. Iron is a metal, oxygen is a nonmetal. So ionic bonds hold it together. Number 6, strontium chloride. Strontium is a metal and chlorine is a nonmetal. So metal, nonmetal is ionic. Okay, number 7 is copper pipe, just made of copper atoms. And so it's just made of copper atoms, so that's copper is a metal. And so if there's at least, 2 metal atoms here, this is going to be metallic. Metallic bonds are holding it together. Brass, which is an alloy, which means a mixture of 2 metals. Brass is a mixture of zinc and copper. Zinc is a metal, copper is a metal, so again, that's metallic bonds. Alright, number 9, H2O. So this is water. Hydrogen's a nonmetal. Oxygen is a nonmetal. So this is held together by covalent bonds. And finally, number 10, which is a molecule called methane. Carbon is a nonmetal and hydrogen is a nonmetal. So this is covalent bonds. So I hope that section kind of makes more sense now. You just got to look at what kind of atoms are there and whether it's held together by ionic, covalent, or metallic bonds. All right, let's move on to number 11. This is about naming ionic compounds. So we spent a lot of time learning how to name ionic compounds. So let's go through it. Number 11, this is going from the formula to the name. So they're giving us a formula here, NaCl, and they want us to name it. Well, we learned that you never change the name of the first one. So Na, we're just going to call it by its name, which is sodium. And Cl is chlorine. Now, how do we change the name of the second element here? Well, we change the suffix to IDE. So it's sodium chloride. Remember to switch that suffix to IDE. Number 12, we've got calcium and nitrogen. So let's name it. So we never change the name of the first one. It's just calcium. Nitrogen, though, we change it to nitride. All right, number 13 is lithium, and we have oxygen. So we just name the first one lithium. Don't change its name at all. The second one is oxygen. So we change it to oxide. Okay, 14. Now be careful with 14. Zinc is a transition metal. So we're going to have to kind of follow those transition metal rules. But zinc is one of the transition metals that we always know the charge of. Zinc is always going to be a +2. So when you name it, you don't have to use parentheses and Roman numerals. We just name it zinc fluoride. Okay. Number 15. Now, this is one where we have to pay attention. So we've got copper and nitrogen. Copper is a transition metal. So we've got to remember to name it with the rules according to the transition metals. So we're going to have copper, but we don't know its charge. So we're going to have to put its charge in parentheses in Roman numerals. And then we're going to name nitrogen nitride. So everything's done except for now we have to figure out the charge of copper. And if you look on the periodic table, it's a transition metal. We're not for sure what the charge of copper will be. So how do you figure it out? We have to look at the other side of the compound. So nitrogen is a -3 charge. I've only got one nitrogen here. So total on the right side of this compound, it's a -3. So the charge times the number of atoms, so -3 times 1 equals -3. Now the thing about ionic compounds is that their charges will always sum to 0. So when you add up their charges, it's got to be 0. That means if the right side is -3, what does the left side have to be? Well, hopefully you're thinking to yourself it has to be +3. Because +3 minus 3 equals 0. They've got to sum to 0. So if this side's total is +3 and we have 3 copper atoms here, what charge times 3 is equal to plus 3? And the answer is plus 1, because plus 1 times 3 is plus 3. So when you name it after the charge of one of the atoms. So plus 1. How do we write a 1 in Roman numeral? Well, it's just a line down. So it's copper 1 nitride. All right, let's go to 16. We've got iron and we've got oxygen. Iron, again, guys, is a transition metal. So we've got to use the transition metal naming rules for this one. So let's write down iron. And it's a transition metal, so I need parentheses. And I'm going to tell people its charge. And oxygen gets changed to oxide. Again, I'm going to separate this compound into a left side and a right side. The oxygen always has a -2 charge, times the 3 oxygen atoms that we have, that's a -6. So we know that the left side has to be +6. But I've got 2 iron atoms here. So what charge times 2 is equal to +6? And hopefully you're saying to yourself +3, because +3 times 2 is +6. So when you name it, we're naming it after the charge. That's going to be iron 3 oxide. 17. Now be careful with 17 as well. Although lead is not in the transition block on the periodic table, it's one of those that we don't know its charge. So we're going to have to name it with transition metal rules. So let's name it. So PB is lead. It's going to have parentheses. We're going to have to tell people its charge. And nitrogen gets changed to nitride. So now we're done, except for we need to find out the charge of lead. Again, let's go back. Nitrogen is a -3. Times 4 is a -12. So that means the left side has to be +12. We've got 3 lead atoms. So what goes here? What times 3 is +12? And hopefully you're saying to yourself +4. So when you name it, 4 in Roman numerals is IV. So that's lead 4 nitride. Number 18. Aluminum, and we've got chlorine. Aluminum is not a transition metal, so let's just name it aluminum. And then chlorine we change to chloride. And that's it. I think if you just pay attention to whether or not it is a transition metal, also tin or lead, if you pay attention to those ones and name them with Roman numerals, it's pretty easy. Okay. Let's go down to the next section, which is on naming again. But this one, they give us the name and they want you to come up with the formula. So on number 19, it is beryllium fluoride. So I hope that you have access to a periodic table. You're going to need one. So if you don't have yours out, please get it out. And you're going to have to tell me the charge of beryllium. And what I always said in class was to write the charge above the name. So beryllium is +2. It's in group 2. And fluorine is a -1. And if you crisscross this, okay, and then we've got beryllium is Be, and the 1 would come down. So you only bring down the number. But we don't write 1s in chemistry. They're implied. So it's just Be, and then fluoride is fluorine, and that's a capital F, and the 2 is going to come down here. So BeF2. And that's it. We can't reduce a 1 or a 2, so there's my answer, BeF2. Now let's go to 20. Lead Iv Oxide. Remember, the IV is Roman numeral. That means its charge is +4. So I'm going to write +4 above the lead. Oxygen is a -2. So let's crisscross it now. Lead, its symbol is Pb. The 2 goes down there. And oxide is for oxygen. And the 4 is going to come down here. Okay, now be careful with this one. Can you reduce a 2 and a 4? And the answer is yes. They're both divisible. They both go into each other. So 2 can go into 4 2 times. So when we reduce it, it's going to reduce to Pb1O2. So with ionic compounds, if you can reduce it, you've got to reduce it. All right, number 21. Magnesium chloride. Magnesium, if you look on the periodic table, has a charge of +2. Chlorine has a charge of -1. Always write the charges above it. Then we crisscross it. Magnesium is Mg. The 1 goes there. We don't need to write it. Chlorine is Cl, and the 2 will go down there. So magnesium chloride. 22. We've got lead 2 bromide. The 2, again, is telling us the charge of iron. So +2 above it. Bromine is a -1. And when we crisscross that, iron is Fe. The 1 goes by the iron. Don't need to write it. Bromine is Br. And the 2 goes down by the bromine. And it can't be reduced, so we're good. FeBr2. 23. Lithium oxide. Lithium, if you look on the periodic table, is a +1 charge. Oxygen is a -2. Let's crisscross it. Li and the 2 goes down by the lithium, so Li2. The oxygen is O and the 1 goes by it. So Li2O. 24. Boron oxide. Boron, if you look on the periodic table, is +3. Oxygen is a -2. So when we crisscross it, boron has a 2 down there by it, and the oxygen has a 3. 2 and 3 cannot be reduced, so there's your answer. 25. Copper 2 chloride. Again, the 2 in Roman numerals is telling us the charge of copper is +2. Chlorine is a -1 charge. When we crisscross it, copper is Cu, the 1 goes there, don't need to write it, and chlorine has the 2 by it. So CuCl2. 26 is iron 3 chloride. Again, this 3 in Roman numerals is telling us the charge is +3. Chlorine is a -1. Crisscross it. Iron is Fe. The 1 goes by it. Chlorine is, the 3 comes down by chlorine, so iron 3 chloride is FeCl3. Okay, very easy. Always write the charge above the name and then crisscross it, and it will be pretty easy. Remember to reduce when you have to. All right, let's go to the next section, which is on naming polyatomic ions. So if you don't have your polyatomic ion sheet out, please get it out. There was a couple of things with polyatomics that's different, and actually they're actually a little bit easier. We never change the name. You never change the name when naming polyatomic ions. So you just look it up on your chart and you have it. Let's go through some examples. 27. Na is sodium. We never change the name of the first one. Now here is our polyatomic ion, OH. There's 2 atoms here, so that's why it's polyatomic. And the OH is a polyatomic ion. If you look it up on your chart, it's hydroxide. And we don't change the name of it, we just name it sodium hydroxide. 28. We've got Ba parentheses OH parentheses 2. So we never change the name of the first one, that's barium. And OH again, it's hydroxide. So it's called barium hydroxide. 29. Again we have Ba, so that's barium. But this time we've got SO4. If you look that up on your table, SO4 is called sulfate. Okay, and I know it doesn't end in IDE, but for polyatomic ions we never change the name. We just write it down. Barium sulfate. Number 30. We've got aluminum. And we've got another sulfate. SO4 is sulfate. Don't change its name. We just name it aluminum sulfate. 31. We've got KNO3. The K is for potassium. The NO3 is polyatomic. That is nitrate. 32. Let's go over this one. You'll see NH4 is polyatomic. That's the only polyatomic ion that actually has a positive charge. So it's listed first as the cation. So when we name it, again, we don't change its name. We just keep it the same, which is ammonium. And then the NO3 is nitrate. And that's it. So in a lot of ways, naming polyatomic ions is actually easier. We just look it up on the chart, don't change its name. Alright, let's go to the bottom of this page in number 33. This time, we still have polyatomic ions, but we're going from the name, so I'm going to give you the name, and I want you to come up with the formula. Same thing though, potassium cyanide. Above the name, I want you to write the charge. Potassium is +1, and cyanide, if you look on your polyatomic ion chart, has a charge of -1. So when we crisscross it, potassium is K, and cyanide is Cn. Now, usually with polyatomic ions, we'll have parentheses around them. But if it's just a 1 coming down, so there's a 1 right here, it's not going to make a difference. So chemists will not use parentheses if it's just one polyatomic ion. Alright, so just KCN. Now let's go to 34. Beryllium Acetate. Beryllium, if you look on the periodic table, has a charge of +2. Acetate, this polyatomic ion, has a charge of -1. So when we crisscross it, beryllium is Be. The 1 is going to go there. Now acetate's polyatomic, and we're going to have a number greater than 1, so we got 2 of them coming down. So you need to put in parentheses. Acetate's formula is C2H3O2. Close it off with the parentheses, and the 2 comes down on the outside of the parentheses. So always make sure that you put the number on the outside of the parentheses. Alright, let's go to 35. Lead Iv Sulfate. The IV is telling us the charge of lead is +4. And sulfate, if you look on your chart, is a -2 charge. Let's crisscross it. Lead is Pb. That 2 is going to go there. Now we have a number greater than 1, so we need parentheses. SO4 is sulfate. And we've got a 4 on the outside. Now be careful. This is an ionic compound. If you can reduce, you should. So we've got a 2 and a 4. We never change what's connected to the polyatomic ion. So this 4, we don't change it. But we can reduce this 2 and the 4 that's on the outside. They can reduce to Pb1 SO4, and the 2 has got to go on the outside. So that's Pb parentheses SO4 parentheses 2. Alright, let's go to 36. Cobalt 3 phosphate. So cobalt 3 has a charge of +3. We're getting that from the Roman numeral. Phosphate, if you look on your chart, has a charge of -3. So we're going to crisscross that. Cobalt is CO. We've got a 3 coming down. Phosphate's polyatomic, so it's PO4 is its formula. Close it off and put a 3 on the outside. Now, can you reduce? The answer is yes. 3 and 3 are divisible by each other, so this reduces to COPO4. We don't need parentheses because after you reduce it, these are both 1s, and so it's just COPO4. Alright, 37. Silver. hydroxide. So you might be thinking, well, silver is a transition metal. How come it doesn't tell us its charge? Silver is one of the transition metals that we always know the charge of. It's always +1. Hydroxide, if you look on your polyatomic ion table, is a -1. We crisscross it. Silver is Ag. The 1 goes there. Hydroxide is OH. And because it's a 1, we don't need parentheses. So it's AgOH. All right, number 38. This one's a bit tricky, so let's go over it. Ammonium is polyatomic. It's the only polyatomic ion that has a +1 charge, has a positive charge. Okay, and phosphate's polyatomic as well. It has a -3 charge. So when we crisscross this, here's how you would write it. Let's write it down here for some more space. Ammonium is NH4, but it's polyatomic, so I need parentheses around it if there's more than 1. So I'm going to put parentheses around it and put the 3 on the outside. Phosphate, because there's only 1 of them, I can just write PO4. I don't need parentheses around it. And so 3 and 1, I can't reduce. Ammonium phosphate. All right, very good. Let's go to the next page of your study guide. So 39. 39 is about naming covalent compounds. So we just went over how to name ionic compounds. So now let's review how to name covalent compounds. So number 39 is asking you to fill in the table below for the correct prefixes when naming covalent molecules. And if you remember, number 1 had the prefix of mono. So when there's just one atom, we say it's mono. Okay. Let's see if we can see that a little better. Number 2, the prefix is di. Number 3 is tri. Number 4 is tetra. Number 5 was penta, like a pentagon. Number 6 was hexa, like a hexagon. Now number 7 is one that I always struggle to remember. It's hepta, is the prefix for 7. Number 8 is octa, like an octagon. 9 is nona. And number 10 is deca, like a decade. So those are the prefixes. Now let's learn how to use those prefixes. So on number 40, it's naming covalent molecules, and they have their own rules. This one I'm giving you the name, and I want you to come up with the formula. So we've got on 40 carbon monoxide. So if there's just carbon, we know that's just one atom. So we just write down C. And mono means 1, and oxygen means it's oxygen. So I'm going to write O for oxygen, and we just have one of them. So I don't need to write it. It's just CO, carbon monoxide. 41. 41 is nona carbon tetrachloride. Nona carbon tetrachloride. So when we look at these prefixes, nona means 9 and tetra means 4. So when we name it, we got to keep that in mind. Carbon is C. I've got 9 of them. So C9, and chlorine is Cl, and the tetra means we've got 4 of them. So C9Cl4. All right, 42. Hexabromine dioxygen, or dioxide. Hexabromine dioxide. So bromine is Br. We got hexa. So that means 6 of them. So that's Br with a 6 down here. And dioxygen. So that's oxygen with a 2 as a subscript, so it's di. So Br6O2. 43. Phosphorus trichloride. Now if there's nothing in front of it, of the first one, that just means 1. So phosphorus is P, and trichloride, and so it's PCl3. Number 44. Octanitrogen pentafluoride. So we've got octa and we've got penta. The nitrogen is just N. Octa means 8, so N8. Fluorine is F, and we've got pent of them, so 5 of them. So N8F5. Okay, number 45. Number 45, 46, and 47. We talked about these in class. They have common names. So water, everyone knows what water is. It's H2O. It's not named with conventional naming. That would be dihydrogen monoxide. It's named with the common name. So water is H2O. And that one's easy because we're familiar with it. But 46, we're not so familiar with this molecule, ammonia. Ammonia is NH3. So whenever you see that, we just name it ammonia. It's not nitrogen trihydride. Okay, let's go to 47. Hydrogen peroxide. Hydrogen peroxide has the formula of H2O2. There's a hydrogen per every oxygen. So there's 2 oxygens, so we have 2 hydrogens. Hydrogen peroxide. All right, 48. Now I'm giving you the formula, and I want you to name it. So we've got sulfur and oxygen, but there's 2 oxygens, so we just name it sulfur. If it's just one, we don't put mono in front of the first one. That's just something we don't do. Ones are kind of implied there. But for this oxygen, we need di in front of it because there's 2 of them, so it's dioxide. So sulfur dioxide. 49. Now it's not a 1, it's a 2 in front of the first one, so we do need dinitrogen. And there's just 1 oxygen here, so it's mono. But we name it dinitrogen monoxide. 50. We've got 1 carbon, so we just name it carbon. So just carbon. And we've got 4 chlorines. So 4, the prefix is tetra, so tetrachloride. So carbon tetrachloride. All right, 51. We've got 2 nitrogens, so that's dinitrogen. And we've got 5 oxygens, so pentoxide. So dinitrogen pentoxide is how you would call that one. 52. We've got nitrogen, but there's 2 of them, so dinitrogen. And we've got 4 oxygens. The prefix for 4 is tetra. But when it's oxygen, we just name it tetroxide. So dinitrogen tetroxide. And finally on 53, we've got oxygen. And we have 2 fluorines, so we're going to name it difluoride. Okay, so oxygen difluoride. All right, now let's go to naming acids. We went over this in class, and I showed you how to name them in class. But I'll tell you right now, I'm only going to test you on 2 of them. Okay, you've got to know the name of 48 and 53. So those are the 2 acids that I'm going to test you on. But let's go over them. So on 48, HCl, this one's called hydrochloric. So hydrochloric acid. is HCl. It's a very common acid, so that's why I'm going to require that you just memorize that one. HCl is hydrochloric acid. 49 I won't put on the test, but let's name it with the same convention that we did 48. So HBr would be hydrobromic acid. Okay, number 50. Let's go and talk about 50 and 51 for a second. 50 is HNO2 and 51 is HNO3. And we went over this in class, but if it has less oxygens, if you look at the polyatomic ion chart for NO2, it's nitrite. And if it ends in ITE, we change the suffix for the acid to us. So this is nitrous acid. Nitrous acid. Now if it's got more oxygens, like this one does, so NO3, it's nitrate. And with acids, you change the suffix ate to ic. And so this is going to be called nitric acid. Okay, so more oxygens ends in ic. If it has less oxygens, we name it with the suffix us, O-U-S. I'm not going to put those on the test though. Number 52, H3PO4. There's a polyatomic ion there called phosphate. And so this is called phosphoric acid. So phosphoric acid. Number 53 is a very common acid, and that's why I'm going to require that you know the name of it. H2SO4. It's got a polyatomic ion sulfate in there. And so 8 has a suffix 8, goes to ic. So this one's called sulfuric acid. Sulfuric acid. Very common acid there. Okay, so that's naming acids. Let's go on to number 54, and it's the diatomic molecules. If you remember, in class we came up with a mnemonic to remember the diatomic molecules. There's 7 of them. The mnemonic that we came up with was, ostriches never fly high in brown clouds. And so the ostriches starts with an O, and so that's for oxygen. So if oxygen is ever by itself, we put O2. So ostriches never, the never is for nitrogen. Fly is for fluorine. High is for hydrogen. In is for iodine. Brown is for bromine. And the clouds was for chlorine. So again, be careful with the diatomic molecules. They have to be by themselves, but if they are, we put a little subscript 2 down there because they are diatomic. Alright, let's go to number 55. And this section is about percent composition. It says, for each of the following questions, find the mass percent of each element in the compound. So let me review how you do this. 55, we've got H2O. When we're doing percent composition, we need the total. The total mass of this molecule. So if you don't have a periodic table out, you should get one, because we're going to be looking up the mass of each one of these elements, the molar mass. Okay, we have hydrogen, which has a molar mass of 1, but I've got 2 of them. So there's 2 plus the 16 from oxygen. So total is 18 grams for this molecule. Now when we do percent composition, we're going to do it for each element in the compound. So we know there's hydrogen in this compound. And so here's how you would do the mass percent. You do the total mass from just the hydrogens, which was 2. And then divide it by the total, which was 18. And then we're going to times that by 100. So grab a calculator. 2 divided by 18. And then times that by 100. and I'm getting 11.1. Let's just round it to the nearest whole number, so that's 11%. Okay. We also have another element in this molecule, though. It's oxygen. The total mass from the oxygen was 16. Just from the oxygen was 16 grams. We're going to divide that by the total, which was 18 grams, and then times it by 100. So grab a calculator, 16 divided by 18, and then times it by 100. So 88.8, let's just go to the nearest whole number. That would be 89%. Okay, and there's my answers. That means that for water, the mass of water, 11% of the mass of water is attributed to the hydrogens. 89, or most of the mass of water, is coming from the oxygen. So again, we're just finding the percentage of the mass of each element in the compound. All right, 56. This is a little larger compound, so be careful with this one. We first need to find the total mass. Okay, so we've got hydrogen, which is 14, if you look on the periodic table, plus the 4 hydrogens. Hydrogen is 1, but there's 4 of them, so there's 4. Plus another nitrogen, nitrogen's 14. Plus we've got 3 oxygens. Oxygens are 16. So let's add 3 16s. So if you do that, the total should come out to 80 grams total. So now let's do the percent composition for each element. We've got nitrogen. Okay. The nitrogen, remember we've got 2 of them. 14 and 14, that's 28. Divided by the total of 80, and then times by 100. So grab a calculator, 28 divided by 80, and then times by 100. And I'm getting 35%. Okay, 35% from the nitrogens. Now, there's more elements than just nitrogen. Let's do hydrogen next. Hydrogen, there was 4 of them, so the total mass from the hydrogens was 4 grams. Divided by the total for the compound was 80, and times by 100. So 4 divided by 80, and then times by 100, I'm getting 5%. Now there's only one more element in this compound, and that's oxygen. We could do process of elimination. We know there's going to be 100% here. And so far we've got 40. So what's left? Well, that'd be 60%. You could just do that, but let's make sure that is in fact the case. So the oxygens, 16 plus 16 plus 16. That'll be 48. So we're going to do 48 divided by 80, and then times by 100 to get our percent. And if you do that in your calculator, 48 divided by 80, and then times it by 100 is in fact 60%. So what you'll notice is that the percentage at the end better add up to 100. If you did it right, it should add up to 100 because you're turning it into a percentage. All right, let's go to 57, last one. So again, we need the total. The total for this compound I got to be 98 grams. Okay, let's figure out the percent composition here. So from hydrogen, that's my first element. The total mass is 2 grams, divided by 98 the total, and then times by 100. So 2 divided by 98, then times by 100, and round it to the nearest percentage, that is 2%. Okay, let's do sulfur. Sulfur, there was only one of them. It's 32 if you look on the periodic table, over 98, and then times by 100. So 32 divided by 98, and then times by 100, is 32.6. So if we round it to the nearest whole number, that's 33%. And now my oxygens, just got to finish that up. There's 4 of them, so 16 times 4 is 64. Over the total 98, and then times by 100. I'm getting 65.3, so let's round it to the nearest whole number, and that's 65. Okay, if you add that together, you will get 100%, and so those are our answers. Okay, very good. Let's go to the next page on our study guide, and that will be problem number 58. Okay. So on 58, it's about balancing word equations. We spend a lot of time in class going over balancing word equations. They're not that easy. A lot of students will struggle with this. So please try these on your own if you haven't first. And then if you need a little help, watch the video. So here we go. Here's what I do. I always write the charge above. So aluminum, if it's just by itself, we're just going to write down Al. Okay, that's just aluminum. Now we've got copper 2 iodide. This 2 right here is telling us the charge of copper is +2. So let's write that there. Iodine's charge is -1. When we crisscross it, let's write down the formula now. It's going to be Cu1 I2. Let's see if I can make it a little better on the video here. Okay, so hopefully you can see that. Now those are our reactants, so we draw the arrow. Now we've got aluminum iodide. Aluminum's charge is +3, iodine's charge is -1. Let's crisscross it. Aluminum just has the 1, the iodine has 3. And then plus copper. Copper is just Cu, and if it's by itself, you should always ask yourself, is it diatomic? So is aluminum and copper diatomic? And the answer is no, so we're just going to leave them. Okay? But now we have to balance it. So let's balance this problem. So what I do is find the arrow and draw the line down. We've got aluminums, copper, and iodines. Okay, on the left side we have 1 aluminum, 1 copper, 2 iodines. On the right side we've got 1 aluminum, 1 copper, and 3 iodines. And so when you look, our aluminums are already balanced, our coppers are already balanced, but our iodines are not. The left side has 2, the right side has 3. So when you ever have a 2 and 3, think of the lowest number that 2 and 3 will go into. The lowest number that 2 and 3 will go into, their least common multiple, is 6. So we're going to try to get to 6. How do you get to 6 iodines on the left side? Well, you'd have to put a 3 here. But by putting a 3 there, we've got 3 coppers now and 6 iodines. Now let's try to get to 6 iodines on the right side. So far we have 3, so we better put a 2 right here. That gives me 2 aluminums and 6 iodines. And so you'll notice my iodines are now balanced, but my aluminums and my coppers are not. So let's do aluminum. How do you get to 2 on the left side? Well, you got to put a 2 as a coefficient right there. And so now we've got 2 aluminum, so they're balanced. The copper, I've got 3 on the left and only 1 on the right. So let's put a 3 in front of this one, and that gives me 3 coppers. And so now aluminum's balanced, copper's balanced, and the iodine's balanced. So there's my answer. But let's make sure we can't reduce any of these coefficients. 2, 3, 2, 3. And they're as reduced as they're going to get, so there's your answer. Okay, let's go to 59. We have just magnesium, so just write Mg. And it's not diatomic, so I don't need to write a little subscript 2. Plus iron 3 nitrate. Iron, the 3 here is telling us the charge of iron is +3. Nitrate is not nitrogen. Be careful. This is not just nitrogen. If it was just nitrogen, it would be called nitride. But it's not. So that's a clue that it is a polyatomic ion. So pull out your polyatomic ion chart, and nitrate has a charge of -1. Let's crisscross it. Iron is Fe. The 1 goes there. Now this is polyatomic, so NO3 needs to be put in parentheses. This 3 goes on the outside of the parentheses. Okay, let's go to the right side. Magnesium nitrate. Magnesium has a charge of +2. Nitrate we just went over as -1. We crisscross it. It's going to be Mg. And we need parentheses. NO3 is nitrate. And the 2 better go on the outside. Plus, my iron just by itself is Fe. It's not diatomic, so I'm just going to leave it Fe. So we quickly look and no, it's not balanced. So let's try and balance this one. We've got magnesiums, we've got irons, we've got nitrogens, and we've got oxygens. Keep it in the same order on the other side. And now let's go through the numbers. We got 1 magnesium on the left, 1 iron. Now careful here. How many nitrogens do we have? This 3 gets distributed to everything on the inside. So we really have 3 nitrogens and 3 times 3 oxygens, so that's 9. Okay, be careful with that. 1 magnesium, 1 iron. How many nitrogens? Well, there's a 2 on the outside, so that gets distributed, so there's really 2 nitrogens and 6 oxygens. Okay, so my magnesiums are balanced, my irons are already balanced, but my nitrogens are not. Again, we have 3 and 2. Whenever you see a 3 and 2, think about the lowest number that they will both go into, which is 6. So how do we get a 6 on the left side? It's really like there's a 3 here. So what times 3 is 6? Well, we need to put a 2. That changes my irons to a 2. That changes my nitrogens. 3 times 2 is 6. And my oxygens now, 3 times 3 is 9, times the 2 as the coefficient, that's 18. Okay, so that fixed my nitrogen to 6. Now on the right side we wanted to go to 6. How do I get to 6 nitrogen? There's really like a 2 right here. So we need to put a 3 as my coefficient. That gives me 3 magnesiums though. Now nitrogen is really 2 times 3, so that's 6. And my oxygens, it's 2 times 3 is 6, times 3 is 18. And that last one just kind of worked out. So my magnesiums are not balanced anymore. I need to put a 3 here. Now they're balanced. My irons are not balanced anymore. I need to put a 2 there. And now they are balanced. And everything else is balanced. So there's my answer. 3, 2, 3, 2. Again, you cannot reduce any of those, so that is the final answer. All right, let's go to 60. 60 says hydrogen gas and nitrogen monoxide react to form water and nitrogen gas. Okay, this is a good one. So let's go over it. If it just says hydrogen gas, that just means it's just hydrogen. Okay, so we're just going to write H. It's pure hydrogen. However, if you ever have an element just by itself, you should ask yourself, is it diatomic? And the answer is yes, this is diatomic, so you need to put a little 2 there. Again, only if it's by itself. What do you write for and? Well, that means a plus sign. Nitrogen monoxide. Now this is a covalent molecule, so let's go through it. Nitrogen is just N, and monoxide, mono means one oxygen, so there's just one oxygen there, so NO. React to form. If you see that phrase, that means there's a chemical reaction, so we're going to show an arrow. Water, that's the common name for H2O. And means a plus sign. It's reacting, or it's forming something else as well. And nitrogen gas. Nitrogen gas is just pure nitrogen, so just put N. However, it's an element by itself. Ask yourself, is it diatomic? And the answer is yes, it is diatomic. So we're going to put a little subscript 2 there. Now, if you look at it, it's not balanced. But we've got the formulas down, so now let's just balance it. We find the arrow, draw the line. We've got hydrogens, we've got nitrogen, and oxygen. Put it in the same order on the other side. Now let's go through the numbers. I've got 2 hydrogens so far on the left, 1 nitrogen and 1 oxygen. On the right, I've got 2 hydrogens, 2 nitrogens, and only 1 oxygen. Alright, so my hydrogens are already balanced, but my nitrogens are not. So I need to get 2 on the left. So let's put a coefficient of 2 there. That gives me to 2 nitrogens, but it also switches my oxygens to 2. So now I need to get 2 oxygens on the right. Well, I need to put a coefficient of 2 there. That gives me to 2 oxygens, but it does give my hydrogens to 4. Now let's go back to the hydrogens because they're not balanced. How do I get 4 on the left side? You need a coefficient of 2 right here, and that gives us 4. Okay, now my hydrogens, nitrogens, and oxygens are all balanced. There's my answer. Now, 2, 2, 2, and 1 are my coefficients. Can I reduce them? And the answer is no, because 1 is already reduced as far as it will go. So there's my answer. Alright, now let's move into the final portion of the study guide. I've got a few problems here on stoichiometry, limiting reactants, and percent yield. We spent quite a bit of time in class going through problems like this, so this is our last chance to finally get it. If you haven't already worked these problems, please stop the video and try them on your own first and see if you can't get them. Okay, so let's get started. I'm going to go through them kind of quickly. They're long problems, so please pay attention. Alright, on 61 there's a few parts, so we've got to solve. Here's my reaction. Now the first thing that we should do is make sure that it's balanced. We've got 2 iodines on the left, 2 on the right. 5 oxygens plus 5 more is 10. We've got 10 oxygens on the right. We've got 5 carbons and 5 carbons. So yes, it is balanced. You always want to make sure that your chemical equation is balanced. Now, let's start. 61A, it says 80 grams of iodine 5 oxide. So we've got 80 grams of this guy. Reacts with 28 grams of carbon monoxide. So there's 28 grams of carbon monoxide. Determine the mass of iodine. So we need the mass of iodine, which could be produced. So we want the mass, which is grams. We want the grams of iodine. Okay, so these two reactants are going to react and they're going to form the products CO2 and iodine. We want to know how many grams iodine that it will form. The problem here is we don't know which one of our reactants is going to run out first. Is it going to be the iodine 5 oxide or my carbon monoxide? So we don't know. So what I'd like you guys to do first is to write down theory. So in theory, how many moles of each one of these reactants do we have? So we look at the chemical equation here. I always put the one with more moles. So this one has 5 moles of carbon monoxide. I put that on top. So 5 moles of CO. And we're going to do a mole ratio. We only have 1 mole of the I2O5. Okay, and let's put a number to that. So 5 divided by 1 is exactly 5. So what that means is that in theory, for every 1 mole of the iodine 5 oxide that reacts, there should be 5 moles of this carbon monoxide that will react with it. So now what we've got to do is determine our actual numbers. So I write actual, and now it didn't give us grams, so we're going to have to take these, or it didn't give us moles, so we're going to have to take our grams and switch it to moles. So I'm going to put 80 grams of I2O5 and put it over 1. Okay, let's switch this to moles. If you've got your roadmap, I would use it. So we're going from grams of a reactant to moles of a reactant. If grams of I2O5 is on top, I'm going to put it on the bottom. 1 mole of the substance, I2O5, goes on top. Now all we need is the molar mass for I2O5. And if you look up on the periodic table, the molar mass of I2O5, let me see if I can get a periodic table here. Okay, so excuse me, I was just grabbing a periodic table. So the molar mass of iodine is 127. So 127, and we've got 2 of them, so times it by 2 is 254. Plus we've got 5 oxygens, so 16 times 5. Add them together and I get 334. So that's a very large compound in terms of mass. So let's, now my grams of iodine 5 oxide will cancel out and I'm left with moles. So let's do 80 divided by 334, and that is 0.24 if you round it to 2 decimal places. And now that is moles of I2O5. So that's one of my reactants. I need to go to moles of the other reactant. We're starting with 28 grams of carbon monoxide. Put it over 1. Let's switch this to moles. So grams of CO has got to go on bottom. 1 mole of that substance is going on top. So we need, how many grams are there in 1 mole? Well, carbon is 12 and oxygen is 16. So that's, let's see, 28. All right. So now my grams of CO cancel out. So 28 divided by 28 is exactly 1 mole of carbon monoxide. Okay. And so now that I have the actual moles of my reactants, I'm going to write actual right here. And we're going to do an actual mole ratio. Now notice how I put moles of CO on top. So my moles of CO better go on top again. So we actually had 1 mole of carbon monoxide and 0.24 moles of I2O5. So let's put a number to that. Take 1 and divide that by 0.24, and I'm getting 4.17. 4.17. That's my actual mole ratio. So when you get that, we're going to compare it to my theory mole ratio. This number is too small. We want it to be 5, because according to the balanced chemical equation, there should be 5. So now, let's think about this. What's making this number too small? If we had more of the top substance, which was CO, would this answer go larger or smaller? So if the top number gets larger, the answer will get larger. Do we want that? And the answer is yes. We need more CO. So what that tells us is that carbon monoxide is our limiting reactant. Okay. So that's kind of a lot of work to determine what your limiting reactant will be. What that means is that we don't have enough carbon monoxide and it will run out first. All right. Now let's go to part B. Well, actually, we still haven't answered everything in part A. So if carbon monoxide is my limiting reactant, it wants us to determine the mass of iodine which could be produced. So now we're going to use some stoichiometry here. I'm going to come over and do the stoichiometry over here. If we know that carbon monoxide is my limiting reactant, we're going to base my stoichiometry off of it. So we have 1 mole of CO. So I'm going to start my stoichiometry with 1 mole of CO and put it over 1. Now we're at moles of a reactant, so if you're following along on the road map, that's moles of reactant. We need to go across the road map. Moles of CO is on bottom, and moles of iodine, the product that we're going to, goes on top. Now where do I get my numbers from? I get them from the balanced chemical equation. We had 5 moles of carbon monoxide and 1 mole of iodine. Now it wanted mass, not moles. So let's go to mass here. In 1 mole of I2, how many grams of I2 are there? And so go back to your periodic table. Iodine has the molar mass of 127. So 127 times 2 is equal to 254. Okay, I know it's kind of small. Hopefully you can see that. 254 was my molar mass. All right, so there's my stoichiometry. That will tell me how many grams of I2 we will form. So 1 times 1 times 254. And then we're going to divide that by 5. Is 50.8 grams of I2. So 50.8 grams of I2 is my answer for part A. All right, now let's go to part B. It says, if in the above situation only 1.6 moles of iodine was produced, what mass of iodine was produced? So if there was only 0.16 moles of it, let's change that to mass. So we want the mass of iodine. So I'm going to put 0.16 moles of iodine over 1. And now it's just basic stoichiometry, just one step. If moles of iodine is on top, we're going to put moles of I2 on bottom. In 1 mole of iodine, how many grams of I2 are there? And the answer was, go to your periodic table. Iodine has the molar mass of 127. So 127 times 2 is 254. Okay, now my moles of iodine cancel out, so I'm going to cross out those units. Now all we have to do to get grams of iodine is times these top two numbers together. So 0.16 times 254 is 40.64, and my units are grams of I2. And so that's my answer. That's how much was actually formed. Now let's go to the second part of B. It says, what percentage yield of iodine was produced? So we talked a lot about this in class, but percent yield is equal to your actual yield divided by your theoretical yield Your theoretical yield goes on bottom, and then we're going to take that number and times it by 100 to get a percentage out of it. So it's very easy. All you have to do is my actual yield for iodine was 40.64 grams. My theoretical yield is what you should form in theory. We determined that earlier up here. In theory, we should form 50.8 grams of iodine. And that's according to my balanced chemical equation. We should have formed 50.8 grams. So we take those two numbers and then divide them and then times it by 100 to get your answer here. Okay, so 40.64 divided by 50.8 and then times it by 100 is exactly 80%. So what that tells us is that we formed 80% of the product that we should have formed according to our balanced chemical equation. So 20% didn't form, and there's a lot of reasons for that. Maybe something went wrong. Maybe we lost a little bit of the reactants. Maybe we lost a little bit of the products. We don't know, but there's a lot of reasons for why it could go down. All right, let's go to the final page of your study guide. Okay, number 62. For this one, it says zinc and sulfur react to form zinc sulfide according to this equation. So Zn plus S goes to ZnS. Let's go to the problem here. If 25 grams of zinc, so we've got 25 grams of it, and 30 grams of sulfur, so those are my numbers, 25 grams of zinc and 30 grams of sulfur, are mixed. On part A it says, which chemical is the limiting reactant? Okay, so we need to find out the limiting reactant. Which one runs out first? Alright, so as with all of my limiting reactant problems, I hope that you're starting with theory. So in theory, we have 1 mole of zinc for every 1 mole of sulfur. And notice they were both 1-to-1 ratio. So it doesn't matter which one you put on top here. It doesn't matter. But we're going to be consistent throughout. So if we put moles of zinc on top, we're going to keep it on top. 1 divided by 1 is exactly 1. So in theory, my mole ratio was 1. Now we just need to figure out my actual mole ratio. However, it didn't give us moles, it gave us grams. So we're going to do a little bit of stoichiometry here. 25 grams of zinc, put it over 1. Let's switch it to moles. If grams of zinc is on top, we're going to put it on bottom, and 1 mole of zinc goes on top. So in 1 mole of zinc, how many grams are there? So let's go to the periodic table, and the answer is 65. Okay, so my grams of zinc canceled out. I hope that you're crossing out those units. And so 25 divided by 65 will give you your answer. And so I got 0.38 moles of zinc. And now let's switch my sulfur to moles. We're starting with 30 grams of sulfur. Put it over 1. grams of sulfur needs to go on the bottom. We're going to put 1 mole of sulfur on top. So how many grams are in 1 mole of sulfur? That's its molar mass. 32. So 30 divided by 32 will give me my answer, 0.94 moles of sulfur. Okay, so those are my actual mole numbers. Now we're going to do my actual mole ratio. Notice I put zinc on top, so I'm going to keep zinc on top. So 0.38 moles of zinc on top and 0.94 moles of sulfur on the bottom. So 0.38 divided by 0.94 gives me 0.4 for my actual mole ratio. Notice this number is too small when you compare it to the theory. It should have been 1. So then we ask ourselves, what's making it too small? If I increase this top number for this zinc, would my answer go up or down in this math equation? Well, if the top number goes up, the answer will also go up. So yeah, we need it to go up. We need more zinc in order to get a mole ratio that was represented in the theory mole ratio. So we need more zinc. What does that tell us? Well, zinc is limiting reactant. So there's your answer for part A. Part B, how many grams of zinc sulfide will be formed? So we want grams of zinc sulfide. This is a product. I want grams of it. Now, when you get to this point, you're going to start your stoichiometry with the limiting reactant. Zinc was my limiting reactant. So let's go to moles of zinc up here. We're going to start it with 0.38 moles of zinc. Put it over 1. Now you can use your road map. We're at moles of reactant. We're going to go across the road map to grams of the product. Okay. Moles of zinc's on top. We're going to put it on bottom. And we're trying to go to moles of zinc sulfide. So I'm going to put that on top. Where do I get these numbers from? The balanced chemical equation. You'll notice that all the coefficients are 1. Now my moles of zinc cancel out. I'm to moles of zinc sulfide, which is a product. But I can't stop there because it wanted mass, or grams. So moles of zinc sulfide goes on bottom, and grams of zinc sulfide goes on top. In 1 mole of zinc sulfide, how many grams is that? Well, let's figure that out. That's the molar mass. So zinc has the molar mass of 65. So 65 plus the sulfur is 32. And so it has a molar mass of 97. Now my moles of zinc cancel out, and I'm left with grams of zinc sulfide, which is what we wanted. So let's times that across. So 0.38 times 97. And I'm getting 36.86. 36.86, and that'll be grams of zinc sulfide. So if you're getting a number close to that, you've done it right. I did round a little bit, which makes my answer not as precise as it could be, but if you're getting a number close to 36.86 grams of zinc sulfide, you're doing it right. Okay, let's go to part C. It says how many grams of the excess reactant will remain after the reaction is over. This is a really good problem, and students struggle with this one. So we want the grams of excess reactant. Well, my excess reactant for this one was the opposite of my limiting. So my limiting was zinc. My excess reactant was sulfur. But we can't start my stoichiometry with moles of sulfur because not all of it's going to react. So where do we start? You always have to start, what I always do is figure out how much the product we are going to form from the limiting. Okay, and we did that. We started with limiting reactant and we went to product that can be formed. So what I'm going to do is start it with 36.86 grams of zinc sulfide. Now what I'm going to do is work myself back across the roadmap and go back to grams of sulfur. And what that will tell me is the amount of sulfur that was actually reacted, the amount of sulfur that was actually used. So let's do that. So if grams of zinc sulfide is on top, we're going to put it on bottom. We're going to put 1 mole of zinc sulfide on top. Now we found the molar mass of this already. It was 97. We found it up here. It was 97. So my grams of zinc sulfide is now canceled out. I'm to moles. Well, now let's go back across the road map. And so we need a mole ratio here. Moles of zinc sulfide goes on bottom to get it to cancel out. And I'm trying to go to moles of sulfur because that's my excess reactant. Now, where do I get these numbers from? That's the balanced chemical equation. And you'll notice that all of my coefficients were 1. And so my moles of zinc sulfide cancel out. I'm to moles of sulfur. Well, I want to go to grams of sulfur. So in 1 mole of sulfur, how many grams of sulfur is that? Well, the molar mass of sulfur is 32. Moles cancel out, and I'm left with grams. Let's times that across. So 36.86 times 32, and then divide it by 97. And I'm getting the answer to be 12.16 grams of sulfur. Now you might be tempted to circle that and say that that's your answer, but it's not your answer. This was grams of sulfur actually used in the reaction. So how do we figure out how much remain after the reaction is over? How much is just left there? Well, we started with 30 grams of sulfur. So 30 grams is what we started with. We used 12.16 grams. How much is left? So 30 subtract 12.16 gives me the answer of 17.84 grams of sulfur. And I'm going to put left over. So 17.84 grams of sulfur will just be left over because it doesn't react. So hopefully that kind of gives you a better idea of how to solve a problem like that where it asks you how much of the excess is left over. Start with what you formed from the limiting, go back to your excess reactant. That will tell you how much you actually used. Take what you started with, subtract what you used, and that gives you what is left over. Okay, let's go to the last problem in the study guide. Number 63. Okay, it says solid calcium carbonate, which is CaCO3, is able to remove sulfur dioxide from waste gases by the reaction written below. And it says here, it is balanced as written. So we're going to assume this is balanced. It says other reactants and it says other products, but that doesn't really mean anything to us. The elements or the compounds that we're looking at are listed here. And let's just assume that they're balanced as written. Okay, so let's go to the problem. It says, in a particular experiment, 255 grams of calcium carbonate was exposed to 135 grams of sulfur dioxide in the presence of an excess amount of other chemicals required for the reaction. Part A says, what is the theoretical yield of calcium sulfite? So theoretical yield means how much should we actually form of this product, calcium sulfite, which is right here. So we want to go to grams of this product. But before we do that, we have a problem because we don't know which one of these reactants is going to run out first. So we need to first determine the limiting reactant and then use the stoichiometry from the limiting reactant to figure out how many grams of this product we will form. Okay, so let's do that now. Hopefully, you're writing down in theory our theory mole ratio. Well, I'm going to put calcium carbonate on top. Okay, so we have 1 mole of CaCO3 on top for every 1 mole of sulfur dioxide. And so in theory, we have a mole ratio of exactly 1. Well, what do we actually have? Well, we don't know because it gave us grams. But we can use stoichiometry and switch it to moles. So 255 grams of calcium carbonate, put it over 1. Let's quickly switch this to moles. Grams of calcium carbonate's got to go on bottom, and 1 mole of calcium carbonate goes on top. So now be careful, all we need is a molar mass. So in 1 mole, how many grams is that? That's the molar mass. And calcium carbonate, I'm getting that it's 100 grams. Okay, so 255 divided by 100 gives me 2.55 moles of calcium carbonate. Well, that's one of my reactants. Let's do the other one. 135 grams of sulfur dioxide. Put it over 1. Okay, my grams of SO2. So that's the molar mass of SO2, and I'm getting that is 64. If you find that on the periodic table, it's 64. So now we just take 135 and divide it by 64, and I'm getting that that's 2.11 moles of SO2. All right, and so now we can do our actual mole ratio here. So my actual, and notice that I put moles of calcium carbonate on top, so I'm going to keep it with that on top. 2.55 moles of CaCO3 on top, and 2.11 moles of SO2 on the bottom. So now let's divide those numbers and see what my mole ratio actually is. And I'm getting my mole ratio is 1.2. So 1.2. Now, let's compare those two numbers. In theory, it was 1, but in actual numbers, we got 1.2. So this is too big. So, let's ask ourselves, why is it too big? If we had more of the top number, if we had more calcium carbonate, what would happen to this number? Well, if we had more of the top one, it would go up. We don't want that number to go up. It's already too big. So what would happen if we added more of the bottom number? If we had more moles of SO2, this number, if you divide by a larger number, the answer gets smaller, which is what we want. We need more SO2. So that means SO2 is our limiting reactant. Okay. Well, that's not really what it asked us to find, was it? We wanted the theoretical yield of this product. So how much product can we form? Now we've got to go back and do some stoichiometry. But it's important to know which one is limiting. SO2, or sulfur dioxide, is our limiting. So when we do our stoichiometry, we're going to base it off of the moles of our limiting reactant. I'm going to come up here. I'm kind of running out of room. So I'm going to take this 2.11 moles of SO2 and put it over 1. Now what I'm going to do is we're at a reactant right now. We're going to go across the roadmap 2 grams of this product. So let's do that. Moles of SO2's got to go on bottom. And we're trying to go to moles of calcium sulfate. SO3, CaSO3 on top. Now, if you look in our balanced chemical equation, the mole ratios are 1 to 1. Okay, so now my moles of sulfur dioxide is gone. I'm to moles of calcium sulfite. Well, I want to go to grams of calcium sulfite. So let's take it a step farther. In 1 mole of calcium sulfite, how many grams of calcium sulfite are there? And that's the molar mass. So let's see what our molar mass of calcium sulfite is. So I'm getting that it's the molar mass is 120 grams. So we had 1 calcium, which was 40, sulfur is 32, and then the 3 oxygens, they're 16 apiece. So yeah, 120. My moles, everything cancels out except for my grams of calcium sulfite. So when we times that through, 2.11 times 120 is 253.2 grams. Now that is the answer for part A. Okay. So that is my theoretical yield. According to the balanced chemical equation, we should form 253.2 grams of the product, calcium sulfite. Alright, now we can go to the final problem on the study guide. It says on part B, if only 198 grams of calcium sulfite was isolated from the products, what was the percent yield of calcium sulfite? So percent yield, let's write that down. It's equal to my actual yield divided by the theoretical yield, and then we're going to times it by 100 to get a percentage. So my actual yield is what it said here. If we actually only formed 198, so 198 grams is my actual yield, we're going to divide that by the theoretical yield. We found that it should be 253.2 grams. Let's divide those two numbers and times it by 100 and get our percent yield. So 198 divided by 253.2, and I'm getting that is about 78% if you round it to the nearest whole number. So my percent yield was 78%. And that's it for Chapter 1. I know that was a long study guide, but we spent a lot of time on Chapter 1. Hopefully that makes sense. If you guys ever have any questions, please feel free to come in and ask me, and I'll help you out.